All right. ECFEST continued. We're going to switch it up to nitrogen nucleophiles now. We got new functional groups coming. 2 new functional groups. If you had to define an imine, what would you say the definition of an imine is? Something that has a C with a double bond to N. If you had to define an enamine, I'd have to say you did. You're done. It has an ene, and one of the carbons of the ene also has an amine. Done. But it's a new functional group. It has its own behavior. It's unique. It's not a mean behavior. It has its own chemistry. Similarly for enamine. Imine. I was talking about enamine. Imines also have a name in biochemistry. Biochem. They're called Schiff bases. Not a reference to a certain California politician, no. Schiff bases does some chemistry. My favorite example of the Schiff base is when retinal reacts with a protein in your eye called opsin and makes a purple chemical called rhodopsin. You ever seen a rhododendron? R-H-O-D, rhododendron. Beautiful purple flowers. Rhodopsin, beautiful purple. There you go. And it's a Schiff base because it's an imine. The nitrogen is double bonded to the former aldehyde of retinal, and it became an imine. So we're going to do a smaller version of this right here. And I want to do the 2 mechanisms simultaneously because they start, the first step's identical, the first intermediate's identical, the next step is identical. It's only at the very end that they have to diverge because the pi bond happens in different spots, right? In one of them, you have to remove a hydrogen from the nitrogen. And in the other, there's only one hydrogen removed from the nitrogen. The other hydrogen comes from the, I'd have to say the alpha position, wouldn't you? The alpha position here is missing an H compared to over here. So that's where you're taking the H. Question number 1, though, is where's the catalyst? Where is the catalyst? And the answer is amines are stronger nucleophiles. Stronger mu. That's a nucleophile of bovine origin. And here we have stronger nucleophiles. So cat not necessary. Cat not necessary. So we have a primary amine. That combination of aldkete and primary amine is imine. Okay? Reminder, it works for aldehydes or ketones. That's why I'm saying this. Same story over here. Works for aldehydes and ketones. So if you start with an aldkete and react it with a secondary amine, you don't get an imine. What do you get? You get an enamine. But both reactions involve reaction of molecule A plus B to make a bigger molecule while losing water. A plus B, bigger molecule water. So they're both fitting in what category? Condensation reaction. Yeah, we went with this one before. Nucleophile attacks the carbonyl. You don't need to activate because the nucleophile's kind of activated. And I won't combine any steps the first time I do it. Won't combine any steps the first time I do it. Equilibrium, equilibrium. Iso CO minus. Iso CO minus. New bond, new bond. Nitrogen, 2 H's, ethyl, plus. Nitrogen, 1 H, 2 methyls, plus. Well, if you use a ketone, you're just going to have R here and R here. And you would have R here and R here. That's the ketone result. I'm going to get rid of it because it's just confusing, right? Yeah, and sorry about that because you didn't hear her question was if you use a ketone, do you get the same result? And you do, but you're going to have a new carbon group off this carbon on everything you drew. Now, here's what's going to happen. This O minus needs to grab one of these H's, but it can't reach them. Why can't it reach them in the same molecule? Yeah, you just got to look at the molecule. As it's trying to reach, there's going to be a partial bond starting, right? What size ring did you just start to make when you made a bond from here to here? 4. We generally don't do mechanisms where you're doing a transition state that is a 4-membered ring. It's too strained. That O minus really can't reach that H. It needs to get it from a second molecule that's identical. So you need 2 copies of this molecule. Okay? So what I was going to do is draw the second copy of the molecule right above that and do it, but I don't want to do that. There's a short form. It's a new short form. It says, you acknowledge that O needs to grab the H from a second molecule. Do you want to show me to show you how I show that? You draw a normal arrow to the H, but you have to write this little word here. And that's as short as you're allowed to make it. Really, that's a short form already. What's it a short form for? Intermolecular, which means between 2 molecules, correct? So you're saying, yeah, it happens, but not with this molecule and itself. That H is from a second one of the same identical nature. And then you finish it off with your other red arrow, which is, you don't have to write intermole on that. That's just happening right there. So that's a nice little short form. You don't ever have to copy the molecule twice. Just use this short form every time. And this is the first time it's ever happened, so it's a brand new deal. But every time you do it, if you don't want to lose a point, you write intermole on the arrow that would be between 2 molecules. There you go. And we're going to draw the result. So far, mechanism's identical, right? You got to like that. And we got an iso COH, new bond to nitrogen. That has an H and that. Got a lone pair. And same story over here. Iso O with an H, new bond to nitrogen, 2 methyls, lone pair. Nitrogen lone pair is so reactive as a either a nucleophile or there's a lone pair resonating. It's reactive enough to kick off a poor leaving group. You can't do this with oxygen. What I'm about to do, if this was oxygen doing this, it doesn't happen. But nitrogen's lone pair is so pushy. I said it like that because you're going to hear that on videos a lot. Pushy, it can kick off a poor leaving group like hydroxide. Kicking off a poor leaving group like hydroxide. And this one's almost done, isn't it? I could have combined steps here. I really could have. But I wanted them to be identical up to here. That's why I didn't combine. Double bond to N. They are identical up to here, aren't they? Same arrows. And hydroxide was produced, very important because you need to use it. Oh, I couldn't combine steps. I didn't have hydroxide yet. I see. No, that's not hydroxide. That was water. You kicked off this poor leaving group. Not normally doing that. That leaving group in each example is a base. Do you agree? Bases love grabbing protons. I think you can see the imine happening right now, can't you? Acid base, done. Imine, acid base to the H on the N. Lone pair becomes, sigma becomes lone pair. And done. Yeah, and there's your water too. What H needs to be grabbed to make the enamine? You can use your Greek letter if you want. It's one away from a C double bond to N. You can also call that the Greek letter alpha. There is an H on this carbon that needs to be removed. And then you resonate to finish. Oh, that's the difference right there, isn't it? That's how the nitrogen got neutralized in this one. Resonance. The other one was straight up acid base. This one's acid base and resonance. Because the nitrogen was out of H's to lose, right? No H's to lose. Those are methyls. And that finishes that one up. So, imine, enamine.